Hey students, in this video we're going to be talking about the mean value theorem, one of the fundamental theorems in differential calculus. All right, so let's explain the mean value theorem. So imagine we have 2 points, A and B. So I've labeled A and B to be 2f of 2, so that's what, 2, 5, and -3. That should be -3. So -3, 0. It's not going to change the result, but we're going to like line up. So we have those 2 points, right? So there's this line. We see this purple line that connects -3, 0 to 2, 5. So when we started calculus, we call this line a secant line. Intersects a curve twice. It goes through 2 points. The slope of this secant line is also what we call the average rate of change. The average rate of change we know to just be the slope of the line, which is f of b minus f of a over b minus a. Now, what the mean value theorem tells us is that, so now I'm going to turn on this tangent line. So I'm going to just move it on the interval from -3 to +2. At somewhere in this interval, because the function is continuous and is differentiable, which just means the derivative is continuous, the slope of the tangent line is going to equal the slope of the average rate of change. Is going to equal the slope of the secant line, which is just saying that at some point the derivative equals the average rate of change. Now, in box 7, I just made a calculation where we have the derivative evaluated at a point. You know what? We'll make this C so that it's more in line with the mean value theorem. So that's a C. This is a C. We'll make that a C. And that is a C value instead. And so now we're good. And we'll make this f of c instead, because that's what I mean by it. So c is just agnostic; it doesn't really matter. But to be consistent with what we're doing for the other stuff, we'll make it that. So when we move our slider, what we see is that at x equals -1/2, the slope at c -1, which is the slope of this tangent line here, is also 1. Oh, get back there, get back. Okay. So that's what the mean value theorem tells us, that at some point along this interval, if the function is continuous and differentiable, that the derivative has to equal the average rate of change, at least at one value. Where that value is, we don't know, but we do know it's between -3 and 2, but we don't necessarily know the exact value. So the only criteria is that the function has to be continuous on this interval and it has to be differentiable on the interval. So for example 1, clearly x squared plus 4x minus 5 is continuous. It's a polynomial. Polynomials are continuous everywhere. So what we need to find is the slope of the secant line. So we're going to say the slope of the secant line is f of 4 minus f of -2 over 4 minus -2. So f of 4 is 16 plus 16 is 32, minus 5 is 27. So 27 minus -2 squared is 4. 4 minus 8 is -4. Minus 5 is -9. So 24 minus -9. No, I'm sorry, 27 minus -9 divided by 4 plus 2. So that seems like it's 36 over 6, which equals 6. So the slope of the secant line on that interval is 6. Now we need the derivative. So our derivative is f prime of x equals 2x plus 4. And so let's say the mean value theorem, I'm going to need a comma. So the mean value theorem tells us f prime of x is equal to 6 on the interval -2 to 4. So to find that value, we just set the derivative equal to 6. So we'll have 2x plus 4 equals 6. And so 2x equals 2 and x equals 1. Now, clearly 1 is between -2 and 4, so it checks out. So if we wanted to, we could we'll graph this function. Its f of x was x squared plus 4x, was it -5? Cool. And so then we had the points were -2 and f of -2 and 4 f of 4. And what we're looking for is the value guaranteed by the mean value theorem. So in this case, we want that slope of the line was, I think, 6. Did we get 6? So 6x. So hold on a moment. So the slope of that tangent line is 6. So then we have y minus 4 equals 6 times x. I'm sorry, y minus 27. So y minus 27. Because we just need one point that's on that line. So y minus 27 equals 6 times x minus 4. So it's at 6x minus 24. So 6x plus 3. Cool. So y equals 6x plus 3. And if we zoom, all right, so if we zoom out a bit, we can see that the purple line, it contains both of our points. So now, if we move our slider to x equals 1, notice that the slope, oh, that's 1.1. Let's move that back to 1. And so now, if we set our derivative equal to 6, because that's the slope of the tangent line at that point, we see that at x equals, well, c equals 1, or really x equals 1, that we get 0 again. That difference is 0. So what it shows is that these lines, again, are parallel. And again, that's what the mean value theorem tells us, that somewhere on this interval, in this case, it happens at x equals 1, the slope of the tangent line is exactly equal to the average rate of change. So again, that's the mean value theorem. Not a very difficult concept. So for example, 2, let's see. So the average rate of change is going to be, so this time we're going to call it average rate of change. That's going to equal 27 to the 1/3 minus -1 to the 1/3 divided by 27 minus -1. So 27 to the 1/3 is 3, -1 to the 1/3 is -1. So 3 minus -1 divided by 28. So that's 4 over 28, which is 1/7. Now, so that's the average rate of change in the interval. Does our derivative have to equal 1/7? So let's find out. So g prime of x is equal to 1/3 x to the -2/3, which is 1 over 3x to the 2/3 power. So remember that we're still on the interval -1 to 27. Here, the mean value theorem does not apply because g prime of x is not differentiable. So it's not differentiable, which means the derivative doesn't exist at x equals 0. Like, we can't substitute 0 in here. So again, all differentiable means is a continuous derivative. All differentiable means is a continuous derivative. So because the derivative is continuous on this interval, the mean value theorem doesn't apply. All right, so there is a corollary to the mean value theorem called Rolle's theorem. And it occurs when the endpoints of the interval have the same function value. In that case, that's going to mean that the derivative has to be zero. So imagine that we have point A here, and sometime later on we have point B. So we have like the point A, f of A, and B, f of B. We don't know where they are. So just assume the function like goes up and then it comes back down to B. Now the average rate of change is zero because we ended back up at B. We ended up at the same f of B value as f of A. Now the mean value theorem tells us that there's a tangent line somewhere that has the same slope as the secant line. In this case, since the secant line has a slope of zero, what the mean value theorem is going to tell us, what Rolle's theorem is going to tell us is that the derivative has to be zero somewhere inside the interval. So it's just a special case of the mean value theorem. So for example 3, we want to check if Rolle's theorem applies for this function. And the only time Rolle's theorem is going to apply is when the function values at the endpoints are the same. If not, then you can just apply the mean value theorem. So f of negative 2 is negative 2 cubed minus 2 times negative 2 squared minus 8 times negative 2. So that's negative 8 minus 8 plus 16, which seems like it's 0. And then f of 4 is equal to, so that's going to be 4 cubed minus 2 times 4 squared minus 8 times 4, which is 64. 2 times 16 is 32. So 64 minus 32, which equals 0. So in this case, we see that f of 4 equals f of negative 2, which equals 0. Just so we're clear, the endpoint values don't have to be 0. They have to be the same value. So if we got both of these to be 8, Rolle's theorem would still apply. It's just a coincidence that we actually got 0. So here we would say, yes, Rolle's theorem applies. The reason is f of 2 f of negative 2 equals f of 4. And so then the derivative is f prime of x equals 3x squared minus 4x minus 8. And we want to find where the derivative equals 0 on the interval. Does this factor? Factors of 24, that would be negative 4. Yeah, I don't think it's factors. Let's do the quadratic formula. So we have 4 plus or minus the square root of 16 minus 4 times 3 times negative 8 divided by 6. So x equals, x equals. So it's going to be 4 plus or minus, what's that? 32 times 3 is 96 plus 16 is 112. So 4 plus or minus square root of 112 divided by 6. So that's 4 plus or minus 112 is equal to 4 times, what? 2 times 56. So 4 times 29. Nope. 4 times 28. My apologies. So 4 times 28, which is 8 times 14. Okay, so, well, 8 is not perfect square, that doesn't matter. So, but it is 16 times, what, 7? Yeah, 7. So we'll say that's plus or minus 4 square root 7 divided by 6, which is 2 plus or minus 2 square root 7 over 3. So let's check that. So let's make a fraction. We're going to have 2 plus the square root of 7. Was it 2 square root of 7? Divided by 3. So that's 2.4. And that 2.4 value, it falls between -2 and 4. And I imagine if we made this minus instead, we're going to get the other value. So both of the values actually fall between -2 and +4. But we can actually see that. Let's graph this function. So x cubed minus 2x squared minus ax. So x cubed minus 2x squared minus 8x. And we'll turn these other things off. So we have a maximum here. And look at the value that we have in box 9. It's the -1.097. It's just absolute maximum. And then if we change that back to a plus here, we're going to get the other value 2.431 if we round to 3 decimal places. So we can see Rolle's theorem applies. And the last thing is an application of the mean value theorem. So any calculus teacher at some point is going to show you this famous speeding problem. So a police car sees somebody start driving, they radio ahead to an officer 30 miles away. When the car reaches the location, the second officer, the car reaches the second person 28 minutes later, and their clock going 60, but the driver was still given a ticket for going faster than 60 miles per hour. Why is that true? So imagine that we have a function where, so we'll want velocity as our output and time as our input. So the velocity at 0, because the car starts, is 0. And then what we want to know is the velocity at 28 miles. Well, we're going to find the average rate of change. So then we have like 28. We're going to look at distance travel. So at 28 minutes, the person had traveled 30 miles. So what we have is, as a function, we have 30 minus, so this is 30 miles minus 0 miles divided by 28 minutes minus 0 minutes. Now, so 28 is equal to 28 over 60, which is, well, 28 is not equal to that. But 28 over 60 is what? 4 divided into both of those. So 7/15 of an hour. So this is 7/15 of an hour. So the velocity that this person was traveling is 30 miles. The average rate of change is 30 miles divided by 7/15 of an hour. We convert both of these. So that's going to be 30 times 15, which is 450, divided by 70. So that's 450 divided by 70, which is, we got a calculator. 62 point something or another. 450 divided by 7, 64.3. So that is 64.3 miles per hour. So now, obviously, if the person was traveling 60 miles per hour, they would have traveled exactly 30 miles in 30 minutes, or 28 miles in 28 minutes, because it's a mile a minute. But because the person's velocity was 64.3 miles per hour, even though when the next police officer saw them, they were traveling 64, they were still traveling 60. Their average rate of change was 64, and so they were given a ticket. So that's a pretty easy example of how calculus can be used to prove that you were speeding or disprove that you were speeding. So anyway, that concludes our video on the mean value theorem. Again, mean value theorem just means that at some point the derivative is equal to the average rate of change. Thanks.